will record this since we got so many people out. Okay, and today's 9/8. So yes, you're going to take all kinds of measurements. You're often going to measure things like time and distance. You're going to measure mass, and you have to be using the right units. Always, of course, we're using SI, but beyond that, once you start taking measurements, you have to think about both the accuracy and the precision of your measurements. So this, again, should be review. Accuracy is about having the right answer. So if the metaphor we're using is bows and arrows on a target, accurate is getting a bullseye. Accurate is hitting your target correctly. Precision is about the ability to repeatedly get the same value when you measure something the same way. So the example that we use often in chemistry is a beaker versus a graduated cylinder. The graduated cylinder is marked at 2 milliliter intervals. It is a precision instrument. It's got this little doodad to help you line up if you have issues with your eyes like I do and they don't work together properly. That helps you make sure that the surface of your liquid is where you think it is, and you can get a very accurate reading. Well, this is only marked off every 100 milliliters. And if I attempt to measure 50 milliliters using this beaker, well, 100 milliliters. Okay, that looks like it's close, and I'm doing the very best job I can. If I take a measurement with this, wow, that was on the 100 milliliter mark, it comes up at 70. Well, let's try that again. So I'll put that's a little over 100 because the other one was so low. So I'm going to go ahead, oh, now I'm over 100. So I've taken a measurement of a volume of water twice with the same instrument, and I've gotten 2 wildly different readings. Let's try it a third time as I spill water all over the place. I can do it right this time, right? Of course I can. Man, I am like right on the 100 there. Eye level reading. And I'm getting 85. This is not a precision instrument. Precision is about using the same instrument in the same way to make the same measurement 3 times, and your values should be boing, 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 right together. Ding, ding, ding. All your arrows are in the same place. Now, this also didn't give me an accurate measurement, you'll notice. This one, if I measure 100 milliliters with this 3 times, maybe I take the mass of that water to determine how close the volume of water that I've measured each time is. My masses should be within, 100th of a gram of one another. Because this is a precision instrument. It's got much smaller markings. It should be much easier to get a volume of water measured that is both accurate and precise. They talk about things like precision machining. If you're creating a machine that's going to do a task repetitively, you want it to do it exactly the same way every time, so that if it cranks out 10 million widgets, every single one of those widgets is identical. Because if those widgets are part of a larger machine and they're going to have to be replaceable, they better be identical. So if you look at like machine science and machine shops, the tolerances for making those items are generally within like a 10,000th of an inch. And in this country, they still use standard measurements. I don't know why. But that's something that you can't really even perceive that with the naked eye as a difference. The parts have to be that alike. That is something that is precise. Now, if your part is supposed to be 3.5000 centimeters, and all your parts are 2.989 centimeters, and the parts are identical, they're precise, but the parts aren't the right size. So accurate, the gold standard, the thing that we always want is accuracy and precision. We want to have the right answer, but we also want to be able to measure it the same way every time. If we are able to get the measurement repeatedly, but it's wrong, it's the wrong value, how do we know that we're not at the right value? Unless we have a known correct value, we can't determine that. If things average out to about the right answer, that's great, but they're so all over the board, what if we only took 2 of those shots? Of course, the thing that we want to avoid at all costs is being neither accurate nor precise, at which point you might as well send a drunken chimpanzee to take your measurements as well as you, because you're not getting the right answer and you're not taking them carefully to make them precise. Questions on accuracy versus precision. Okay, so which one, and you can just do you know sign language? A is like a fist with your thumb up. I'm only going to teach you 2 letters. A, fist with thumb up. P is the walking person. Try it. A, P. A, P. Okay, so which one is about getting the right answer? Give me an A or a P. Accuracy or precision? Awesome. Yes, accuracy. What if all my values are tightly clustered after I measure something, but they're not actually the correct value? A or P? P, walking guy. Okay. Good. Thank you for playing along with me with sign language. So, let's talk about accuracy first. There are 2 reasons that your data can be inaccurate. One is your fault. The other is the fault of your instruments. So, method error. If I measure 100 milliliters of water with the graduated cylinder and with the beaker, do I have the same volume of water? Probably not. So I've used 2 different methods to get my sample, and so that's going to introduce some method error. When you measured in your lab, when you measured diameters and heights, and you devised multiple methods, did you get exactly the same measurements for each method? No. So you could have one method that is substantially less accurate than another, and overall your data is going to be flawed. So we tend to want in science to take the data the same way every time, because that way we can evaluate the accuracy and the precision of that one method. Being sloppy. We've all been there. Honestly, the first time I measured the volume of water, I probably wasn't as careful as I could be. I got a lot closer on the last one, being really seriously careful, but the instrument's still crud. So I still didn't get an accurate volume. There is something called parallax. Who here has watched Star Trek? Or I'm sorry, Star Wars. We were talking about Star Trek this morning. Okay. Physicists always roll their eyes and groan when they say that Han Solo ran the whatever it is in so many parsecs. Because a parsec is not a unit of time, it's a unit of distance. And they use it incorrectly in the film, which science people get all up in arms about. Parallax is the difference in, okay, you got to focus on this one. Parallax is the difference in the apparent position of an object based on the distance between the observers. So if Connor and I, who are however many meters apart we are both looking at the same thing, and we're going to perceive its position slightly differently based on the distance between us. Now, it's not that big a deal in the classroom, This has been used to, well, this is actually how we estimate the distance to a star. Because we can look at observatories on different parts of the planet, know the distance between them, and then look at the difference in the perceived position of the object, and we can figure out how far out it is. So I would invite you all to take your thumb and cover up something in this room. Close one eye. Okay, so I'm covering up my little plant. Hold your thumb out at arm's length. Cover up something. Now switch eyes. Does your thumb jump? It should. Close one eye, then the other. Does the thing suddenly show up? That's parallax. The difference in position, now the distance between your two eyes is not all that great. For some, I have heard, and I don't know the truth of this, and I've never asked an anatomist, but I have heard that some people have a bigger parallax error than others, and some people's eyes don't actually work together well. So if you're somebody who can't target shoot with both eyes open, or can't look through a microscope with both eyes open, you're in the club. It is a source of error. I do woodworking, and I always have to close one eye to take measurements because my eyes don't create one image, they create two. Fun little thing. So I close one eye, but if I close different eyes, guess what? My measurement jumps. So I can mark the same piece of wood twice and get different measurements. So that's parallax error. Now, those are all your fault. That whole top category is the fault of the measurement taker. The bottom is instrument error. And instrument error isn't your fault, but you have to pay attention to your instruments to make sure that you don't have instrument error cropping up. For instance, and we will not use the beam balances in here, we use them in chemistry. These beam balances are highly precision instruments. They're great. And you have to make sure that they're zeroed before you use them. And you have to make sure that the little number on the pan and the number on the hanger match the number on that, or it'll never balance. And you also have to make sure, and this is one of the ones that was tampered with years ago, this metal tray on the bottom, if you take the screws out, there are a bunch of little BBs and washers in there that they put in at the factory to get the balance. And years ago, we had a year-long sub in a science classroom who pretty much let the kids do whatever the heck they wanted. And two young men took it upon themselves to bend back the metal trays on the bottom of these while she wasn't looking and remove BBs. We found little BBs all over the place for years. So we then had a whole set of those that we couldn't get to balance, and we had to remove the metal face pieces, and you can purchase a kit from O-House, and you can make them work again. That's a damaged instrument. That instrument is never going to give you an accurate reading. The other thing to watch out for, you used these nice antiques the other day, the wooden meter sticks. So these meter sticks take some abuse, and if you look carefully at the end, this one probably, at least on the corner, the last two marks are missing. They've been worn off over time. When I'm taking measurements with one of these, I generally start at the 10 centimeter mark, because I know that that hasn't been worn off, and then I just have to remember to add 10 to whatever measurement I get. That's where pilot error comes in. So I'm compensating for what I know is a damaged instrument, but then I can also make a method error and forget to add my 10 back in. So those are all sources of inaccuracy. So now we're going to talk about precision and instrumentation. So do you have a book? You've got your iPads on the desk in front of you. Excellent. I'm not going to beat you with it, I promise. There's a meter stick. And Connor, you get that one. Don't share that with anybody else. You'll see why in a second. Okay, Kitty. So I want you, with the instrument that you have been given, to measure the length and width of your iPad. Yeah. There you go, sir. You're welcome. Tell you what, Juan, I'll have mercy on you.
Thank you.
There you go, sir. So measure the length and width of the iPad. What's the matter, Luke? Don't you dare tamper with that instrument. Kitty and Luke, you seem to be struggling.
We just gotta be smarter.
You have to be way smarter. Okay. So what I gave Kitty and Luke is a hard time. I'm going to take a picture of this. So instead of a regular meter stick, what they got, now I want to take a picture. Take a picture. There we go. What they got looks like that. It just looks like a green stick. I covered it in painter's tape. So there are no marks on this thing whatsoever. Now I could make one that had marks on 10s or something. Maybe I'll do that some year. If you have one of the regular meter sticks, I'll tell you what, Melanie, I'm going to take a picture of your meter stick as a contrast, because you got one of the nice ones. These are heirlooms, artifacts from the old school. There we go. These lovely heirloom artifacts are marked down to the what? So what is the lowest division of measurement that shows on this? What are the units here? So this is a whoops. This is 1 centimeter. You are correct. But what's the smallest division on there? Millimeters. So if we zoom way in, that is a millimeter. Now the question is, if I have something, if I have an object, and I measure it, and it is ending right there. What am I going to record as its length? So it starts right here, and it ends right there. So what am I going to record as its length? Sorry? 1.55 centimeters. Okay, that's one answer we've got. So I got 1.55 centimeters.
15.5 millimeters.
You could record 15.5 millimeters. Either of those are legal. Both of those are correct, because you get one more place than the smallest marked increment on the device. What does that mean if the object in question, and we'll do a different object here, is that long? So it goes from here to exactly there. Now what would we need to record? So I have a vote for 1.1 centimeters. Any other votes? And do you see a difference in the measurements we recorded here and the measurement we're recording here?
3 significant figures.
Yes.
1.10.
1.10 centimeters. That's really important. When you start taking measurements, because I do grade on sig figs in physics pretty much from day one, and when you're doing a lab where you're taking the measurements, somebody will say, well, where do we get our sig figs from? Because usually they come from the given. If you're the one who took the measurements, your sig figs are determined by the instrument you used. And so when we get into forces, we do a lab with some spring scales. And we have 4 different kinds of spring scales, and they have different smallest increments. So you have to make a note of which one you used so that we know that your sig figs are correct, because these are going to determine the precision of your measurements. Okay, so that's when you're taking the sig figs from your own measurements. When you're handed a set of numbers, you have to assume that they recorded their sig figs correctly, and you have to maintain those sig figs. There are rules for determining whether or not a number is significant, and there are rules for maintaining your sig figs in calculations. I'm going to have you guys review those tonight, and when you walk in tomorrow, we're going to do, let's see, we'll do a survey on sig figs, and then we're going to do a quick wrap up and go back to, yeah. So I'll take these, you can put them back on the table if you'd be so kind. So review page 17 and 18 in your text tonight.